Testing. Okay. Apparently there was no sound. Let's try that again. So my name is Scott. Oops. Now I'm hearing it. Test, test. Okay. Now it seems to be working. Nope. How about now? Okay, let's try this again. My name is Scott. I am from the University of South Florida. This is calculus. Today we are going to be talking about L'Hopital's rule. The test is coming up. Of course, I'm going to go over the quiz in just a moment. There were technical difficulties. For some reason, the thing could not hear my microphone, but then when I turned on my microphone and made it hear that, I heard feedback through my headset. I have no idea why. That will be a mystery that I solve later today. I solved it right now by just muting the stupid thing. So if you talk to me, I can't hear you, but that's typical anyway. Today we're going to be going over last time we went over optimization. Today we are going to go over L'Hopital's rule. Tomorrow I'm going to try something new because I would normally have a problems thing on Wednesday at 5. Tomorrow I'm going to try something new. I'm going to do optimization part 2, an optional live lecture, but I'll do part of the problem set that's due on Friday during that lecture. Of course, it will be recorded. You can watch it, you can not watch it. It's entirely up to you. I will do something kind of cool, but it's not something that's necessarily on the test. But I will do some, things that are also on the test, but nothing new. I'll just do some more examples of optimization problems. And then I'll show you another way to solve them. But of course, that's completely optional and totally up to you whether or not you would attend. I would do it on Wednesday during the normal time. But on Wednesday, we're going to have a test review at 5 p.m. And then on Thursday, as usual, test review at 5 p.m. At 7 p.m. Wednesday's class, we will start Module 4 as usual. We will be doing, starting the new material. The last of the new material will be done today, in the quiz that will be due on Wednesday, and I'll go over on Wednesday. Okay. Are there any questions? Okay, so that's the plan for the class. Let's go over the quiz. Oh, there are questions. Yes. Oh. Okay, so 1 to 5, how do we feel about that lovely plan since, the thinking? Yes, so there are questions about the bootlegs. You may take the bootleg, since we've got Proctorio now, you can take the bootleg just like before. You'll see that there's a quiz on there called bootleg. Normally I let you take it and then you pick it back up and you keep taking it and stuff like that. That doesn't really work. What I've done is I've set up 3 attempts. I've set up 1 already, and then I'll set up the other 2 later. But what will happen is on Proctorio, you'll have, there'll be 3 attempts. You can do 1 of them, you can do 2 of them, and I'll grade the best or the graders will grade the best as normal. You take the bootleg like the quiz. Also on Thursday, I haven't completely settled it yet, but there will be a second pre-assignment due this week, just like before where we had one of them get on Discord. We'll have a new one, which is print up the answer sheet for the test, scan the answer sheet, put your name on it, and scan the answer sheet for the test and upload it to Gradescope. We want to find out If anyone has any issues with PDF scanners, some of them have 10-page limits. We want to make sure that you're on one that works. And we want to just make sure that everyone's got an answer sheet. So you can either print the answer sheet or write your own, but those things will be due on Thursday night with the other pre-assignment. And we'll have the quiz and all that stuff up for that. Are there any other questions? Office hours today are the same time as normal at whatever, 12:30. Any other questions, comments, issues, suggestions, and thoughts? Okay. All right. So if that's it, then let's go over the quiz. So, the farmer. Now, this was just like, believe it or not, the one I did in class. The only major difference was this one had an endpoint, right? I had this wrinkle, right? The wrinkle was that suppose no fencing is needed along the side of the barn, so there we have a price of 0. The fencing along the west side of the plot is shared with a neighbor. Okay. And there's a large oak tree to the north, so that side, this side here, can be no larger than 180 feet. Okay? Fencing costs $20 a foot. Okay, so it's more complicated. There's lots of little things going on here, but let's break it down. Okay? Let's just break it down here. Let me see. How do I do this? There, beautiful. Okay, so here I've got the what I'm going to do is I'm going to do a drawing. Now, adjacent to the north wall, here's my barn, and I'm just going to draw a little, a rectangle north of the barn. Okay. No fencing is needed along the barn. So this side here is free. Whatever it is, it's free. Fencing costs $20 a foot. I have to pay for all of this fence, and I have to pay for all of this fence. Okay? Now, this side of the fence, Canada and I are going to split the cost of the wall. Okay? We couldn't, Mexico, we may pay for their entire wall. But Canada and the United States are going to, share the cost of this one. This side of the wall is $10 a foot because whatever it is, we're splitting the cost. So how do we feel 1 to 5 about the setup for this? Okay. And I have this oak tree that's up here, so I put an oak tree there. And that oak tree is 180 feet away. And that gives me these endpoints. I've now got an endpoint. My minimum L length, right? This is width times length. My minimum length here is 0 feet, right? If I got no fence this way, I'm going all fence that way. However, I'll get no area if I do that, but that's an endpoint. But the other endpoint is L being 180 feet. Okay, I can't make it so that W is 0 because then I'm going to run into the oak tree. So my other endpoint is 180 feet. So I take area is length times width, at least this week. And this is the cost of the fence. It's $10 times this side, $20 times this side, $20 times this side, and $0 times this side, and all of that equals 6,000. So I do some algebra, and I wind up with that width equals 300 minus 3/2 L. I substitute this back into this, and I get this single equation. I get that the area equals 300 L minus 3/2 L squared. And that's going to be what I optimize. So I've combined it into one equation. How do we feel about that step, 1 to 5, the combining? To get one equation. Okay. All right. So now that I've combined all this, right here, I'm going to take the derivative and I'm going to set it equal to 0. Okay? So when I do that, I wind up with 300 minus 3L, right? I take the derivative of this with the power rule. This squared is going to hit that 2 when it comes down, right? It's going to be 2 times 3 halves L squared. I mean, L to the first, which is just 3L, equals 0. And immediately what pops out is that L equals 11 feet. Okay? How do we feel about that 1 to 5? How do we feel about taking the derivative and setting it equal to 0? Okay. Pretty good about that. Now, I'm going to take the second derivative just to check. Okay, while I'm here, I've already taken the first derivative. I'll just take the second one, right? So I take the second derivative, I wind up with -3. That's less than 0. That means that my function is concave down. And that means that right in the middle of my function, I have a little maximum. Okay, so L equals 100 is the max. All right, how do we feel about that 1 to 5? Just a little second derivative test while I'm at it. I didn't wait till the end because I just took the first derivative. Let's do the second while we're at it. And we get that little number. How do we feel about that second derivative test? This is just to ensure I had a maximum. Okay. Now I've got L is 100. I'm going to solve for W. Well, first thing I'm going to do is make myself a note. I'm going to check my endpoints. My endpoint here, L, is less than my maximum. My maximum was 180. L is less. So this endpoint, this oak tree, I'm still 80 feet away from the oak tree. Right? I don't care. Right? Now, the L here. So once I do that, and which variable you get will depend on which one you subbed for. It's perfectly fine to do the other one. But remember that the constraint applies to whatever you called this side. You could have called this side W or whatever, but the constraint applies to the side that is $10 a foot. So this right here had to be the same as that. Now, you could have optimized for this side, but if you did that was you could have optimized for the free side. But if you did, remember your constraint doesn't apply to that side, it applies to this side. It wouldn't have made a difference either way because both of them, 150 is also below 100. But that's the side you need to check for the constraint. If it was 120, it would have mattered which one was which. So I solve for W and L and A, and I wind up with 150 feet for W just by plugging it in. And then I wind up with 15,000 square feet as the whole thing. How do we feel about that? 1 to 5. 1 to 5. How do we feel about that one? Okay. So I wind up with the optimal dimensions, and just like the related rates problems, I'm going to say that the optimal dimensions are W equals 150, L equals 100, and the area. I'm just going to kind of sum it all up together. Not required, but kind of nice just in case there was some interpretation problems. Now, you didn't actually need the second derivative test here. So there were a couple of ways to do the check the max min, okay? I did the second derivative test just because it's easy. You could have just said there's only one endpoint, and that then you could have just thrown the other endpoints. I didn't do that, right? Here, I used the fact that I had a maximum, and that maximum was less than the 180. But you could have computed the area if the length was 180, and the area if the length was 0, and said that this area was bigger. That was another way to do it. You could have also done a first derivative test. That is another way to do it. So there were a couple ways to do this, right? I could have checked my endpoints. I could have done the second derivative test, or I could have done the first derivative test. And all of those would have worked, okay? So 1 to 5, how do we feel about the fact that there were a couple ways to do this? The check to find out I had a max. Okay. Now, notice that I said method 1. There is a method 2, and that's the thing I'm going to talk about tomorrow night at 5 o'clock, or tomorrow evening at 5. There is another way to do these that's kind of slick, but it's not required. And it is in the textbook, but again, not required, not going to be. I mean, you can do the one on the test the slick way. Don't get me wrong. But this is the way, this is the standard approach to solve all of these problems. And I don't want to confuse you if you are, if you like too much information overload thing. So if you're interested, there is another way to do this that's very slick. It's very Calc 3. And there's something on the problem set that we'll be walking through tomorrow night that's on it. Attention, but you don't have to. You have to do the part that's on the problem set, but you don't have to do it that way. There's another way to do it, which is just the standard approach. So that's tomorrow night. All right, enough advertising for that. How do we feel 1 to 5 about this whole problem? And I've put, of course, there's a problem, like there's an optimization problem on the test. I put some information here. So I put and I'll post this key if I remember. I think I remembered to post the notes last time, which was, big for me. But if I remember, I'll post this key, and this key has the rubric for this particular problem. And the rubrics are all just about the same. A couple things, you do get partial credit for setups. So if you totally mess up the problem, write a bunch of stuff about the setup. Draw some pictures, list your variables, do stuff like that. Because there is a lot of partial credit on these, right? Taking the derivative and setting it equal to 0, is... You can get all the things up to that and a bunch of partial credit without having to take the derivative and set it equal to 0. So if you panic or something happens, dig in and do a lot of setup stuff. And heaven forbid, you might figure out the problem. Okay. What's the motto for this test? When in doubt, do what? Okay. How do you know that 180 is an endpoint? You know because you read the setup and you do it with the draw. So there's a large oak tree 180 feet though. So the west side may be longer than 180. This is kind of one of those things that in this case, it doesn't actually matter. You could have ditched the 180 because, you had to say you checked it, but the optimum is going to be in the middle. But think about what costs money. Okay, that oak tree doesn't cost money. Fence is what costs money. And that was kind of the idea from the last thing. And I said that right here, that the trick to these problems, when you're doing the constraints, and I think I even said it in big things, yes. What costs money, right? That's the thing that you have to ask. Draw it and ask yourself what costs money. The big idea was that things cost money. And the thing that costs money is your constraint. So in peer leading, you had tape, right? And you wound up with a square, and then, you made Canada pay for one side of the campsite. So you wound up with not having to pay for that, right? And you could use the same tape. But we had only so much caution tape. What was implicit is that the caution tape costs money, right? I have some sort of budget. The money term had to be in caution tape, but I still had some kind of budget. Same thing for the aluminum can. I wanted to find the thing that minimized when I was building the water bottle, I wanted to minimize the surface area of the cylinder. Why? Because aluminum costs money, right? So I wanted the biggest volume. I wanted the volume, a specific volume, given the surface area that, I wanted to find the surface area that was the smallest because aluminum costs money. Just like before, caution tape costs money. So I wanted to figure out what was the biggest I could do with a given caution tape. So that's the thing to think about on these problems. Just think about what costs money. The water bottle was the one in the in peer leading. There were 2 models in peer leading. One of them was the campsite, and the other one was a better water bottle. It looks like you guys didn't get to a better water bottle. Is that correct? Okay, so if you didn't get to a better water bottle, I'll put it on the I'll put it as one of the options on the problem set, so you can see it. But the idea was all the same. I was minimizing costs. I was minimizing the aluminum needed. Why? Because aluminum costs money. I was maximizing the campsite that I could get with an amount of caution tape. Why? Caution tape is the thing that costs money. So just remember, when you're doing these problems, think of what costs money. And you usually will get them. Okay. Let's go back to the quiz. Now, a couple things happened over the weekend. One of them was that, so did everyone see the study guides I put out? I put out one here. So on the canvas, where it's yelling at me to grade all your work, which hasn't been done yet. And I sent an announcement today about what's going on for the grading, by the way, just in case you want to know where your stuff is. But on here, this is the answer sheet, and I'll talk more about that later. But right here, I put a list of theorems and proof for Module 1. Which was this I thought it was very helpful. It was a student suggested I do it. And it's got the list of all the theorems we talked about, because I know there were a lot of them. Whether or not where they are in the book, whether or not we proved them in class, whether or not it's proved in the book, whether or not you have to state it raw on the test, right? So the question may be, state the intermediate value theorem. Or not the intermediate value theorem, that's not on the state the extreme value theorem, state the stationary point theorem or Fermat's theorem, state Rolle's theorem, state the mean value theorem. All of those are perfectly valid, right? If I said state on test, you might have to state them on the test, straight. Now, we also did this thing where we decided to do a bunch of true-false questions. So what happened was remember when I did, like a couple classes ago, I did Rolle's theorem on a quiz? Because that was on the test. And then they cut it. I actually think it's, I think what they've done is slightly harder, but it is also slightly less Maalox inducing, indigestion inducing. So, either way. So what they've done is I was part of the thing that did it. What we did was we cut the long proof. Now there's still a proof on the test. And then there's also problems that are proofy. But the proof is going to be one of these three things, the just straight proof, right? It's going to be arcsine, arccosine, and arctan. So those are the three proofs you have to memorize, and you only really have to memorize two because arcsine and arccosine are exactly the same. So we did, two of them are on the bootleg, one of them's on a quiz. So you've seen, right, we did, so cut. Now, that means that I'm not going to ask you. So on the test was this beautiful question that said, prove one of the following, your choice, Rolle's theorem, mean value theorem, et cetera, et cetera, et cetera. Okay? Now, cut means that the proof, asking you the proof straight, is no longer on the test. However, some of these things have become true-false questions. Okay? So that's what this purpose of this next question is on the quiz. So some of these things, like diet L'Hopital's rule, increasing, decreasing, first derivative, second derivative tests, all these tests wound up as like true-false questions. Well, not all of them. Some of them wound up as true-false questions. And they can be a little tricky, so let's go over them. The thing that got cut, but I can still ask you like pieces, like, is it the case, right? I could ask you the piece, like assume otherwise, blah, 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 blah. Is this argument convincing or something like that? I don't know. We didn't. But apparently we're supposed to tell you we could have. But there are pieces that could be asked as true-false questions. So let's go over some true-false questions. So there's the diagram. I made a little diagram for you guys. And then I told the other instructors, no, it's my diagram. You can't have my diagram. So, I don't know if they'll still post it anyway. But this is for you guys. So thank the student whose name I cannot mention on the class who suggested I do this, because it was very helpful. Okay, so let's go over it. Now, there's kind of justification area. I'll get to that in a minute. It's totally not required. But let's go for it. F prime of u equals 0, then f has a local min or a local max at u. That's false, right? Because I can have things like x cubed. Now, the idea behind the justification is partial credit. These things are 2 points a pop. So there's a couple of ways to get partial credit on these. One, if you say something intelligent, you can get one of the 2 points, okay? Second, if you mess up one of the other ones, but say a good justification for one of these, you can get refund points. So the thing is worth 2. So if you said true here, you're going to get -2 on your take. But then let's say you did something really nice here. We'll put a +1 and give you up to half the points you missed. Okay, so the idea is that you get the idea is that you can still get partial credit on these. Now, what is this? Fermat's theorem says that if f has a local min or a local max, and if f is differentiable at u, then f prime of u equals 0. So L'Hopital's is not the converse of that is Fermat's theorem. Okay, but that is not Fermat's theorem, right? I can have things where the derivative is 0 and there's no local extrema there. It's a little slick, right? I could ask you the same thing. If f double prime of u equals 0, does that mean that there has to be an inflection point? No. Consider x to the 4th. The double prime is 0, but I don't have an inflection point. And there's one of those on the bootleg that is really good about that. So one of the questions on the bootleg has that stuff. And I'll talk about the bootleg a little bit. But yeah, so these problems can be a little tricky. Okay, so do a little justification because that partial credit's going to save you. And as I said, I actually think this is harder than asking you a proof. Okay, I could have said prove Rolle's theorem and you memorize it and hopefully you understand it, but it's pretty easy to get full credit on it. These are a little tricky, but they're what they wanted. That was the determination. So I said okay, and I made some. Now this one. If f prime of u equals 0 and if f double prime of u is less than 0, then f has a local max. Break down the statement, okay? If f double prime of u is less than 0, that means I'm concave down. So I'm going to draw myself a picture, and then I'm going to go dash, 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 dash. Okay? So if I'm concave down and f prime of u equals 0, yes, I have a local max. That's true. And I justify it by doing a little drawing. Okay? So 1 to 5, how do we feel about part A? I should have asked that. One to 5 on part A. It's a tricky one, I admit. How about part B, 1 to 5? One to 5 on part B. Okay. This one is in your book. If you're, it's on. Oh, where is it? It's in section 4.3. Okay. Now, is it a local max? The point is, remember that local max is the biggest in the neighborhood. So it could be a global max. If this had said f has a global max there, it actually would have been false, right? Because I'm asking about a particular point. Okay, I'm asking about a particular point. So the point is that here I've got the biggest thing in the neighborhood, right? Whereas if it's a global max, it's the biggest thing everywhere. And I don't know that from this little piece of information. Okay. All right. Part C, if f prime of x is greater than 0 on the interval, then f is decreasing. Nope, that's wrong. It's increasing because that's what a positive slope looks like. I said false. 1 to 5, how do we feel about number C there? Okay. All right, if f has a critical value at u, then f prime of u equals 0 or f prime of u does not exist. That's true. Why? Well, that's the definition of a critical number. Okay? All right. I've Noah, and I could say your name on chat, ha 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 ha, because you're an employee. I have no idea what you're talking about the world having only 26 numbers. Please stop that. You're confusing people. So anyway, so anyway, how do we feel about that question? Part D, 1 to 5. Okay, that's just the definition of a critical number. It's a place where the x value is, the derivative of the x value is 0, or the derivative does not exist at that point. Okay. Now, part E. This was that tricky statement. If f prime of x equals g prime of x for every x, then there exists a C so that for every x, g of x equals f of x plus c. In other words, they're vertical shifts of each other. This statement is true. And that statement is corollary number 7 in section 4.2 on page 215. Okay, it's that thing that we proved, and it was one of the options for the proof last time. It's an extremely important statement, and it was one of the options of the proof that was on the test, but it got cut. The proving it bit, not the statement of it bit. The statement of it bit is extremely important. How do we feel about that? Vertical shifts of each other, 1 to 5. This is part E. This statement about vertical shifts. So I'm trying to write on this thing and it's not working. Okay. We feel okay about that. It's an extremely important concept that the derivative determines the shape of the graph. Okay? I can move the graph up or down. Okay? I can move the graph up and I can move the graph down. All right? But I can't do anything else. And yes, you could say f of x equals g of x plus c. You could say either one because c would just be the negative of whatever the other c was. Okay? The important thing is the concept that these things are just vertical shifts of each other. Okay? So here's one here. Right here, this might be f. This may be g. And there's some fixed c. Like this. And that fix, right? That distance between f and g here. That distance between f and g. F and g here is fixed. That height is fixed. Okay? And that's an extremely important concept. Can I say it again? That's an extremely important concept. Okay. Any questions? Okay. Exactly. Yes, there's a comment in chat. That's exactly what I'm saying. All right, 1 to 5. How do we feel about this quiz overall? All right. Okay. And I'll have office hours today. I'll be happy to go over constrained optimization problems until the cows come home. I'm happy to set up more time tomorrow besides the 5 p.m. thing if you guys want me to do more of these examples. If you guys want to work out a few and then talk about them in Discord, I'm happy to talk about them with you. If you want to go over the one in peer leading, I'm more than happy to go over it again with you. The 2 models from peer leading. The constrained optimization, the book has all of these problems that are like, if I have 2 boats leaving at the same time, just forget that, okay? Do the ones where something costs money. I guess gasoline costs money, okay? But if you do those are the ones we actually care about. Now, there's a bunch of them in the book, like Snell's law. You use constrained optimization to prove Snell's law using Fermat's principle, which is different than Fermat's theorem, by the way, which is different than Fermat's little theorem, which is different than Fermat's last theorem. Okay, Fermat has a lot of things named after him. Okay, but you can prove things like Snell's law and all these physics-y things. Who cares? Okay, stick to the things that cost money, because those are those things. Now, will reviews be recorded? No, reviews are not recorded. I go over things in reviews. Okay, so any other questions? All right, before I spin off over to L'Hopital's rule, let me go over a couple of things on the study guide and on this stuff here. So if you pull up the bootleg and if you pull up the study guide, there we go. So here's the official study guide. And if you look at it, I put on here all of the problems. I put the usual stuff, the problems. I added some examples, okay, from the book that you might want to go over. But then what I did was I went through the bootleg. And I went problem by problem through the bootleg and told you how relevant it was to the test and how similar to the test these problems were, okay? Now, question 15. Now, if you look at your answer key, and this is one of the things that, everybody's kind of got a thing up on this one because we also have the answer key. So if you go through the answer sheet, you go through the bootleg, you go through your old quizzes, you can start to guess at what some of these things look like. Okay, this number 1 here, I'll talk about it some more, but that's probably what always comes first. And then what is this? These are popcorn derivatives, right? And I've only asked you 2 because there's only 2 new things we have. And then I've got some more take it to the limit problems. Okay, yes. So the thing always comes first. Then I've got some popcorns. Then I've got some take it to the limit problems. These are L'Hopital's rule problems, or, knowing not to use L'Hopital's rule is part of using L'Hopital's rule, right? I mean, you need to know when not to do it as well. And then we've got some derivatives for you to evaluate. Now, for these, you don't need to prove a trig thing if you use it, okay? So if you're using the derivatives of arcsine, arccosine, and arctan, you don't need to prove those derivatives there. You've already got them, all right? So there's no need to prove those. Those are just like the things. And yes, I am going to cover L'Hopital's rule today. Then you've got some find the absolute mins, find the absolute maxes. Watch for things that are outside the domain. Watch for things where the derivative doesn't exist at the max and min. Those sorts of things are always nice problems to ask. Watch for critical points that are outside that you don't actually care about. Question number 6 here. At 7, you might have a little, something on the bootleg might be similar. Something on the bootleg might be similar. Interpreting derivatives, something on the bootleg might be similar. You must choose one of these. Something on the bootleg might be very similar. Question 10 is a proof. Something on the bootleg will be very similar. True-false questions. We just kind of went over that today. And then 2 graphs. Okay, each one worth 8 points apiece. Expect the graphing problems to be, we instead of having one graph with 16 points, like it was when Noah took it, We have 2 graphs, each one worth 8 points with fewer conditions. So before the graph had like 12 conditions on it. Now we've got 2 graphs, 6 each. So, they're not all stacked on top of each other. And the conditions can be met. It's not like that quiz a little while ago where a condition can't be met. Okay. This one, they can all be met. And I'll go over this more in the test review on Wednesday and then again on Thursday. Okay. But if you go through this and then go through the bootleg and your old quizzes, especially the ones that I told you, if you feel anxiety about this, go through the one where I told you what problems to try on the quizzes. And then, here I've told you what the relationship between the questions. So like on the bootleg, question 2 is, of course, throwback statements, just like not last time. So those aren't on the test, but I want you to keep them in mind because they do wind up on test 3. On test 4. 3, 4, and 5 slightly harder than the ones on the test, and 5 is really long on the bootleg, way harder. Question 6 is like really, really hard. Question 6 on the bootleg requires you to do logarithmic differentiation. We are not requiring you to do that on the test. We are requiring you to take a derivative and set it equal to 0, but you don't have to do a logarithm. 7 is just about playing with functions. So it's about understanding more. And it's really important for the test, especially for the true-false section. But I'm not exactly going to ask you something right on point. Right? I'm not asking you for examples of functions where this is true, this is true, this is true. But on the true-false, you're going to find statements that you can falsify using those as counterexamples. So that was the idea. I want you to play with some functions. You will need to prove one of the inverse rules. There are 2 of them on the bootleg. There's 1 of them on a quiz. So get those. Questions 10 and 11 were cut. Question 12 has a flavor of one, but it's a little easier. It's harder than the one that's on the test, but it's sort of the same flavor. I couldn't stop myself on question 13. That's the one where I asked you to prove that the cube root of 2 is irrational. But it's not on the test, but it's a really cool problem. It's fun. And if you're going to take bridge, if you're thinking about math, 1, get your head examined. 2, that's the kind of problem that you want to be able for. 14 is the optimization. 15 is graphs. I love graphs. Are there any other questions about the test? Okay. So that's all I'm going to mention about the test. And I've given you the thing. Let's go ahead and let's start play with L'Hopital's rule. I've got, I've actually got, some time left. I thought I talked too much. Well, I did talk too much, but I thought I really talked too much. So today, as I said before, we're going to go over L'Hopital's rule. And before test 2, we actually did L'Hopital's rule for the 0 over 0 stuff. Okay, that's a direct consequence of linearization. Let's see if we can make this work again. There we go. Sorry, I've got little technical issues with the sun is changing its, there we go. Okay, so I actually went over this before. So how well do we remember L'Hopital's rule 0 over 0? 1 to 5, how do we feel about it right now? This statement right here. All right. Okay. So we did 0 over 0 before. And remember, this was a consequence of the linearization idea. Okay. So if f of x and g of x both go to 0, then I can take the derivative of the top and the bottom, not the quotient rule, the derivative separate of each other. And I can find and I get the derivative of the whole thing. So as an example here, okay, sine of x. What is sine of pi? Here's 0, here's pi over 2, there is pi. So what is the northiness of pi there? That's 0. So the top goes to 0. Okay? Now, if I plug pi in here, I get pi minus pi. Okay? So that means that the bottom goes to 0. That means I can apply L'Hopital's rule. Okay? So in order to write this, let me go ahead and write it in purple here. So the top and bottom both go to 0. That means by L'Hopital's rule, and this is how everybody does it with the little h on top. Okay, you can put the h on top and everybody knows what you mean. If you look at the solution guides to the book, they all put the h on top. Okay, so what I'm going to do is I'm going to put the h on top because I'm about to apply L'Hopital's rule. I have 0 over 0, right? I have 0 over 0, therefore I can. All right, I can't do this if 0 over 0 if I don't have 0 over 0, but because I have 0 over 0, I can apply L'Hopital's rule. So I take the derivative of the top, the cosine of x, oops, I need my limit sign. And even if I was writing this on the test, even I wouldn't write this step down. Okay, this is me just showing you where it is. So I'm taking the derivative of the top and the derivative of the bottom separately. No quotient rule involved. Okay? And I get the limit as x goes to pi of cosine of pi over the derivative with respect to x of this bit is just 1. Okay? Okay, well, I had a mouse that was, had a scroll wheel in it, and now I don't know what I did with it. Oh, well. So then here, well, the cosine of, I'm sorry, not the cosine of pi, the cosine of x. Well, the cosine of pi, I could directly substitute, right? And I get the cosine of pi over 1. And the cosine of pi equals negative 1. Okay. How do we feel about that, 1 to 5? Okay. The important bits were I had 0 over 0, I had 0 over 0, and the derivative of x, right? The derivative of x minus pi. The derivative of x is simply 1. And the derivative of the sine of x is cosine. So then I directly substitute in here. I get cosine of pi over 1, and the cosine of pi, the eastiness of pi, is negative 1. Okay. Okay. Yes, putting the h over the equal sign is required. You have to say you're using L'Hopital's rule. You can write, using L'Hopital's rule, you can write LH, but the h is required. You must indicate that you're using this theorem. Okay, this is a mega theorem. Okay, it's not one of the little minor rule things where you do it one step at a time. No, this is a major theorem. You have to use it. It's a good question. Notice this does not work if the things went to 0, if the things didn't go to 0, okay? So, for instance, I look at this problem right here, okay? This problem right here, the top goes to what here? The top here goes to 1, and the bottom goes to 0. But 1 over 0 is not indeterminate, okay? 1 over 0, that's an infinity of some sort. And here I've actually got a direction on this infinity, right? 1 over 0 is not 0 left, it's 0 left. 1 over 0 left squared is 1 over 0 right. And then 1 over, so let's talk about this a little bit right here. 1 over 0 left squared equals 1 over 0 right. And 1 over 0 right squared equals 1 over 0 right. So my function actually looks like this. Right? So my function actually looks like this. This thing has a defined, this thing is determined, no L'Hopital's rule, no nothing. This is 1 over 0 plus, 1 over 0 plus is infinity. And that's one of the ones I get for free, right? I get 1 over 0 plus. If you remember way back from the first class, from the first module, I get 1 over 0 plus for free. That one's infinity. Okay? How do we feel about this 1 to 5? Don't use L'Hopital's rule on this. 1 to 5, how do we feel about that? Oops. Okay. All right. So what I'm doing here, okay, if I did try to use L'Hopital's rule, it would screw it up, right? This is in green. Don't do this. Right? If I did take the derivative with respect to x of 1 over the derivative with respect to x of x squared, what would I get? The derivative of this constant would be what? Would be 0, and the derivative of the bottom would be 2x. Right? I'd be in trouble, right? This right here equals 0. 0 does not equal infinity. Right? Even if we go, yeah, man, what happens if 0? No, right? We don't make 0 equal to infinity. We can make negative infinity equal to positive infinity, you know, if we want to smoke that particular brand of bud. But we don't do 0 equals infinity. Okay? So I don't want to do that. Okay? So let's make ourselves a little table. All right? 0 over 0, that's the indeterminate where I use L'Hopital's rule. Infinity over 0, that's determined as long as the left and the right agree. And it does not exist if they don't agree. All right? Infinity over 0 is determined, 0 plus is determined. That's positive infinity. This is negative infinity. And 0 over infinity equals 0. Okay? Not infinity. I take something really, really small, and I put it over something really, really big, and I wind up with 0. Okay? So how do we feel about that? 1 to 5. 1 to 5, how do we feel about that? All right, so this is normal L'Hopital's rule. Okay? And that was that ratio of linearization thing. And it's very important, and I cannot stress this enough, only 0 over 0. Or there's one other form, and this was the form that you got on the problem set. There's an infinity addition, okay? And I'm not going to prove it because it's not on the test, and it's kind of it's one of those proofs that's very technical and not very interesting. There's cool proofs like the ones for Rolle's theorem. There's technical but really important proofs, and then there's technical and who cares proofs. This one's one of the last ones, okay? This one you just know the rule, okay? You know the proof for the 0 over 0. You know the diet proof for the 0 over 0 because you want to have this idea about the ratio of the linearizations, but this is not a proof you want to know. Okay, it's not a proof that, you know, if you take analysis, they'll probably even skip it then. Okay, it's just one of those proofs. You're like, oh gosh, why? It's, you know, it's like one of these 3-page ones. If you want it, it's in the back of the book, but it's one of those really long proofs that's just incredibly boring. And yes, I'm saying that about a proof. I think this one's just incredibly boring. So I'm not doing it. Thank you. You're welcome, right? So, but if I have infinity over infinity, some sort of infinity over some other sort of infinity, I can also apply L'Hopital's rule. Let me give you an example. Okay. So here's the example. The example here is e to the x over x. Yes, I know. It's just this proof. No, there are proofs that I find boring. This is one of them. Okay. So e to the x goes to infinity. As x goes to infinity, e to the x goes to infinity. X goes to infinity. So I could take L'Hopital's rule. Now, if it had been negative infinity over positive infinity, that's also fine too. And you could sort of see where that comes from. You could sort of see where that comes from because if I had 1 over e to the x over 1 over x, I would have a 0 over 0. Okay? So here I've got an infinity over infinity. So I'm going to apply L'Hopital's rule. I'm going to take the derivatives. D over dx, e to the x. E to the x is a little bastard, so I'm actually going to do this. Oops, I'm not supposed to say that on the internet. Someone put a mature rating on my Twitch real fast for this lecture. Okay. So what I'm going to do is I took the derivative of the top and the derivative of the bottom. No quotient rule involved. Derivative of the top and the derivative of the bottom separately. And I wind up with the limit as x goes to infinity of e to the x over 1, and that this top bit goes to infinity, the bottom bit goes to 1, and that is just infinity. How do we feel about that, 1 to 5? Okay. So the big thing is I must have 0 over 0 or negative infinity over negative infinity. Nothing else. Only these two will work. Okay? If I don't have a quotient, and I'll do one of these in a minute, I can put it into a quotient. The third thing is I can do it as often as I want, as long as I can do it as often as I want, as long as I end up doing it a finite number of times. Now I'll get to that in a minute. There's a question in the chat. What if I have undefined over undefined? Do you mean does not? Remember, there's this technical difference between does not exist and undefined. If what you mean is does not exist, then you've got nothing. You need to figure it out some other way, and that can happen. But so an example of that happening is 1 over x over 1 over x as x goes to 0, right? So then I would have d and e on the top, d and e on the bottom. Well, the limit of that whole thing is 1. But I can't use L'Hopital's rule to figure it out because the limits don't exist. So I have to, do a similar equation. I have to wind up with the fact that the thing is just 1. So the question there was, what if I have undefined over undefined? Or what if I have d and e over d and e? Here, this d and e, this d and e, another way. What I'm going to do here is obviously simplify. So use different Okay. Good question. Oops, I screwed it up. You can't see that because I don't have a touchscreen and the monitors aren't linked properly. There we go. Okay. So if I have DNA over DNA, I can't use L'Hopital's rule. I have to use it another way. And you couldn't see me right because I wasn't in the screen. Okay. So the big idea is that I could do it. I'm going to flip back. I know you didn't see this when I wanted you to see it, but I will print the notes and I will show it to you. I do need to move on here. Okay. Let's talk about this last big idea. I can do it as many times as I want. So let's take the following problem. Let's do the limit as x goes to infinity of e to the x over x squared. Okay? Now, the idea behind this problem is I'm going to do just what I did before. I'm going to apply L'Hopital's rule. I get infinity on the bottom, and I get infinity on the top. So I get, by L'Hopital's rule, this equals the derivative with respect to x of e to the x over the derivative limit as x goes to infinity over the derivative with respect to x of x squared. And that equals e to the x over 2x. Oops. That equals the limit as x goes to infinity of e to the x over x squared. Okay, so how do we feel about that? I'm sorry, not x squared, 2x. Duh. How do we feel about that, 1 to 5? All I did was apply L'Hopital's rule. I just applied it once. However, I wind up with a problem that I'm not done with. Okay? Well, this bit right here goes to infinity. This bit right here goes to infinity. So I'm going to do it again. This bit goes to infinity, and this bit goes to 2. That is perfectly determined. That's infinity. Okay. So so what I'm doing is I'm just taking the limit. I'm going to take multiple and multiple derivatives. The idea here is that the first two terms of the Taylor polynomial, right, f of x over g of x were equal, right? They were equal to 0 or infinity. So I went to the next two terms of the Taylor polynomial. And then I went to the next two terms of the Taylor polynomial. And then I went to the next two terms, and I went to the next two terms. I just kept going down terms until I get something that's not infinity over infinity or 0 over 0. Okay? And I can keep applying it, but I can only do it a finitely number of times. Okay? So another example of that. So what would be the end result of this answer here? How many times am I going to apply L'Hopital's rule to get that? Right. How many times is it going to take? Yeah, 5, 6, more than one, right? Right. This one took 2 applications of L'Hopital's rule. This one's going to take 5. It's going to run 5 times L'Hopital's rule to get that. Now, what if I had this one? What if I had something else? What if I had something on the bottom that didn't quite work for this. Okay, let me give you an example. Let me find the example that's in the book, because the book has a good one. The book says, what about this? Is this the one that the book had? No. That one's boring. E to the x. Now what's going to happen? Yeah, so if you do this, you're going to wind up with infinity equal over 5 factorial. That was the answer. Here, yeah, I'm going to have a problem if I apply L'Hopital's rule. This goes to infinity here. But what's going to happen as I go again and again and actually, no. That one's going to be fine because I'll wind up with something. This one will actually, after one attempt, wind up with something that's infinity over 0. That one's fine. Never mind. Noah, come up with one that doesn't work because you have to do it an infinite number of times. Oh. Sorry. That one's fine. There you go. X to the 1/3 over X to the 1/2. Now, if I do it, I'm going to wind up with something. I'm going to wind up with something. I'm going to wind up with when I take it, I'm going to wind up with a negative exponent. But then when I take it again, I wind up with 2 negative exponents. And then I take it again and again and again and again. This would require infinite numbers. Because I keep winding up with exponents. Now, the secret to this one is to do it once, then flip the exponents again. You know, you can do various things. The secret to this, no, it does exist. I just can't use L'Hopital's rule, right? This does exist. Okay? This does exist. This is the same thing as the limit as x goes to infinity, right, of x to the 1/3 minus 1 over 2. Right? And that right there equals the limit as x goes to infinity of 1/3 minus 1/2. Come on, Scott. It's not that early in the morning. That would be 2/6 minus 3/6 would be negative 1/6. And that equals 0. Yep. Right, because that's the same thing as the limit as x goes to infinity of 1 over the 6th root of x, and that equals 0. So yeah, this one exists, but it's algebra. Okay, how do we feel about that 1 to 5? That was a little funky, but the point is that I don't want to use L'Hopital's rule. There's an old joke, right, about the difference between intelligence and wisdom. Intelligence is knowing that a tomato is actually a fruit. Wisdom is not sticking it in a fruit salad. Kind of the same thing, right? You don't want to use L'Hopital's rule on this because you're never going to stop. Okay, you use algebra. There are other ones that you use algebra for, even though you could use L'Hopital's rule. I love those. There's ones that, you can run 4 derivatives of L'Hopital's rule on, or you can do a little algebra ahead of time. Let's go back to that e to the x over x to the 5th thing. Okay, how could I algebra this out first? And let me look at time before I do this. It's a cool example, but I want to make sure that I'm not going to run out of time before I do the other ones. Oops. Okay. So how else could I look at this one? The question is there another way to do that? Okay. Is there a way to kind of get at this algebra? To get at this without doing that L'Hopital's rule thing right away. Let's look at this. I had the limit as x goes to infinity of e to the x over x to the fifth. All right. Now, what happened if I took the fifth root of this thing? Okay. What would happen if I took the fifth root of the whole equation and then took it to the fifth? Well, the answer is nothing, right? Those things are inverses. But let's look at it. Is everyone on board with that? I just took the fifth root of the top and the fifth root of the bottom. And so now I'm taking the limit as x goes to infinity of something to the fifth. Well, that's a continuous function. Taking something to the fifth power is continuous. I can pull it out of the limit. So this is e to the x over 5. I took the fifth root of the top and the fifth root of the bottom. Right? I took the fifth root of the function and then took it to the fifth power. And because taking something to the fifth power is continuous, I can pull the fifth off of the thing. And I now get the limit as x goes to infinity of e to the x over 5 over x to the fifth. So now I'm doing the fifth after I take the things. Okay? Hit refresh on Twitch if your screen is blurry, and it will redo the screen. That happens. I think it happens because Twitch changes your buffering, and if you're on a cable modem, sometimes it does that. And if you hit refresh, it usually fixes itself. Remember, it's a low latency platform, so you don't care about that information. Just hit refresh. Okay. So what happens here? Well, this bit here goes to infinity, and this bit here goes to infinity. I apply L'Hopital's rule, but I only apply it once. So the limit as x goes to infinity, the bottom, right, is 1, and the top becomes 1/5 e to the x over 5. Right? I do the chain rule. Okay. If you want to see that, that was probably too fast. E to the x over 5 times 1 over 5. Chain rule. And that's all to the fifth. So I dealt with the limit on the inside of the parentheses by using L'Hopital's rule. Now this equals infinity. This bit here goes to infinity. This bit here goes to 1. That means that what I've got is infinity over 1 to the fifth, and that just equals infinity. Okay? So I could have done it, L'Hopital's rule, 5 times. But if I sit down and do a little algebra first, I can get away with doing it 1 time. How do we feel about that, 1 to 5? I just did something that was actually very clever on this thing. I mean, I'm not taking credit for figuring out the cleverness. I'm just saying this kind of trick is pretty slick. Okay? So, it's the sort of thing that I would put on the test, but it would be x cubed on the bottom and e to the 3x on the top. And I might do that. I might not, I think I did it last year, so I couldn't get away with it this year. But it's something that I could put on the test where you could apply L'Hopital's rule 2 or 3 times and get the answer. Or you could have done a little bit of algebra first. Now, I was able to take the entire thing to the 5th power because I took the 5th root here. So I took the 5th root of the inside, and then since u to the 5 is a continuous function, I was able to just pull it out of the limit. Again, it's a little slick. Okay, I'm not saying it's not a little slick. Okay. All right. Well, it also means that this algebraic manipulation, I could apply L'Hopital's rule to things that don't look like L'Hopital's rule problems by doing a little algebraic manipulation first. Okay? So let me show you an example of one. All right? This one is in your book as well. It is, let's not do that one. That one's boring. X times the ln of x. Okay, fine. So this one's example 6 in your book. Okay. I read all of these studies, by the way, if you're wondering why I'm going back to the textbook. I read all these studies that said that if you were teaching online, you had to stick closer to the textbook. So I'm trying. I'm trying to do the examples from the book. I'm trying to talk about the examples from the book because, the thing said, all the research said, you're teaching online. Stick to the textbook. Fine. Made me sad. But okay. Example 6 in your book says this. I want to evaluate the following. Now, if I just plug in 0, I wind up with 0 times infinity. And 0 times infinity is indeterminate. Okay? Matter of fact, I'm going to write that on my little chart. I'm going to come back up to my chart and I'm going to say 0. Okay, I'm going to say 0 times infinity, that's indeterminate. Okay? So what I need to do is I need to make it so that I need to make this into a form that I could apply L'Hopital's rule to. So what I'm going to do is I'm going to make it a quotient. How can I make this a quotient? Well, let's rewrite it. Yes, well, I can't really separate it, right? Because the limits don't work, right? I still wind up with 0 times infinity. But I can do this. I call this ln of x, and then on the bottom, I call it 1 over x, because this is really x here, okay? This is really x to the first. So what I could do is I could call that 1 over x to the negative 1. In other words, all I've done is moved a negative exponent to the bottom. Now, if I do that, and I know that's a little bit of algebraic voodoo, but if you think about it, right? 1 over 1/3 is 3. Okay? Yes, 1 to 5. How do we feel about what I just did? That little algebra voodoo. It is voodoo. 1 to 5 on the algebra voodoo. Okay. All right. So what I've done is I've said, right, 1 over 1 over 3. So for example, let's just do a little example. 1 over 1 over 3 equals 1 divided by 1 over 3, right? That's what that means, which is the same thing as 1 times 3. So what I said was I worked backwards. I said x was equal to 1 times x, which is equal to 1 divided by 1 over x, which is equal to 1 over x. I moved this way. Okay, that's how that little piece of algebra magic worked. Okay. But now I've got something. Now this bit here, as I go to 0 plus, that's negative infinity. This right here, as I go to 0 plus, is infinity. Now I can apply L'Hopital's rule. I've got a negative infinity over infinity. How do we feel about that 1 to 5? That I've got now negative infinity over infinity. Okay. All right. Well, now I've got negative infinity over infinity. I'm going to apply L'Hopital's rule, and I get the limit as x goes to 0 plus the derivative of this, which is 1 over x, over the derivative of this, which is what? I'll put the derivative signs up there. Okay. Yeah, I've got negative 1, but remember this is an x to the negative 1, so I subtract 1 from the exponent. I wind up with negative 1x over negative 2. Now what I'm going to do is I'll do a little bit more algebraic manipulation. And I wind up, I'm going to move this x here. This 1 over x is an x to the negative 1. I'm going to move it to the bottom. I'm going to move the negative 1 to the top. And I wind up with x squared over x to the first with a negative 1 on that one. Now I'm going to do a little bit more algebraic manipulation. In other words, I'm going to cancel some stuff, and I wind up with negative x. Okay. How do we feel about that one, 1 to 5? That one's got some algebra involved. Okay. All right. Okay. Yes. That's negative x equals 0. So this is the limit as x goes to 0 plus of negative x, which is the same thing as negative 0, which is the same thing as 0. This is a direct sub. Okay. All right. There's one more weird one. And those are the ones where we have to do an indeterminate power. Okay. So here's one that's off your bootleg. right, well, it's close to the one that's on your bootleg. I think the bootleg is x to the whatever x. Here's one that's very similar. Oh, shoot. Am I over time already? Crap, I am. Okay. I need to do one more example, and then I will go to them. I'm sorry, I went over. I lost track of time. So let's do one more, and that's the indeterminate power. This is example 9 in the textbook. The limit as x goes to 0 plus of x to the x. Okay? And I total loss of track. Okay. So what I'm going to do here, okay, is I'm going to do the exact same thing I did before, but I'm going to take the log, and then I'm going to take the power. Remember that exp and log are inverses of each other. So I'm going to do this trick right here. And if I do that trick, I'm going to wind up with x goes to 0 plus, okay, of exp of ln of x to the x. So that's going to be x to the times ln of x. Okay? Now, this bit right here, I'm going to pull out the exponential, and I wind up with exp of x times ln of x. Now, oops, this should be the limit. Okay? Now, this bit right here we just did. Okay, and this right here is, so what I wind up with is e to the 0, which equals 1. Okay, so this is because exp is continuous. Okay, so that's the last one. That is significantly, there's one like that on the test review, but that is significantly harder than something that's on the test, and that's also how you do the one that's on the bootleg. Okay, are there any questions for me? I went way over, and I'm sorry. Remember that e to the x, recall exp of x equals e to the x. It's just another way of writing the exponential, but I want to do that because I don't want to write an e to the something there. That's just annoying. Any other questions? And again, that's algebraic manipulation of these things. Okay, again, I'm sorry for going way over. I'm going to stop streaming now because I got to do the next class. Thank you very much.